Okay, let's begin. So we are going to pick up with the examples that we had to finish from last time. So let's actually just jump into it. D. And some of these, as you can see, was very similar to the problems on the quiz. So if you did these over the weekend, quiz shouldn't be an issue. How do you do this? Yeah.
Tabular method.
Come again?
The tabular method.
Okay, how would you use tabular method?
You could set e to the x as u.
That's not e to the x, that's e to the x squared.
Well, e to the x squared as u.
Why would that be u? Yeah?
Because when you do the derivative, it turns into 1 over 2x du dx, so one of the x's cancel out on the x cubed.
We do the derivative where?
So he said to set u as x squared, right?
No, he said to do the tabular method with u equals e to the x.
Wait, are we looking at D?
We're looking at this one.
Yeah. I didn't do the tabular method. I did U-sub and then I solved it out.
Yeah. But I'm following his trend. He said something different. So let's explore that in a bit. We might come back to you. Yeah, so tabular method with u being what?
E to the x squared.
Which tabular method, remember, is another way to do by parts. How do we choose the parts in by parts? That was on the quiz.
Well,
That was the answer to that question. Right? What kind of functions are these? This one here? In terms of the letter. That's an A, and this is E. So if we were to choose a U, who would be the U? This guy. Okay. So if you want to jump to tabular method, you're going to let that U be that guy. Now, dealing with that is not going to be an issue. That's 3x squared. That's 6x. That's 6. That's 0. What is the integral of e to the x squared? You can't. That's impossible. Right? Remember, the integral of e to the x squared is not something that can be done. So, no, that is not the step. Let's try to go with this idea. What did you do?
I set u equal to x squared.
Okay. Now, what made you think of that?
Because I was able to see that after you do the derivative of it, you would get 1 over 2x du equals dx, so one of the x's with the x cubed would cancel out, leaving u with x squared, so then you can use u again, if that makes sense.
So that actually does work out, but perhaps we're not all so insightful. So why you would think substitution is because literally it's step 3, and integration by parts is later than that. So you look at this. If tabular method is your first thought, you've already messed up. You're not following the strategy. Tabular method should be step 4 or later. Substitution would have come before that. Now, when you decide to substitute, you're going to consider substitution, right? First thing you think of, remember, going back over the strategy. Is that a basic rule? No. Can I simplify it to look like a basic rule? No. Does a substitution work? Now you start to think, what would I substitute? Is that a viable option? Can this make my life easier? Now, because we know, because I mentioned in class, that this guy here is literally impossible to integrate, I know that e to the x squared is making this thing complicated. I don't want e to the x squared. What's nice? E to the x is nice. Right? See, that guy, I know. This guy, don't know. Right? How do I know this guy? Well, that's one of the rules that Jhevon asked you to memorize over the weekend. So that you know very well. And because we know that we're paying attention to detail, the moment we see something that's off about this rule, for example, that little square right there, it means that this rule is now off the table. There's a problem with that rule. So I know how to deal with e to a single variable as the power, not to the square of some variable. So my first thought is, you know what, that e to the x squared, don't really like it. Right? So, yeah, I'm going to set t equals x squared would be my first shot. Get that e to a single variable. Now I'm using t instead of u because I can kind of see that it's probably going to result in an integration by parts here because the derivative of that is just going to give me an x. I'm going to be left over with x's here, so that kind of tells me that I'm still going to have a product of functions to deal with. So looking ahead, I sort of know that, oh, I'm going to probably this is going to lead me to somewhere else. But I would start off with a substitution. dt would be 2x dx, which means this guy, because this is x squared times x, the x dx is the 1/2 dt. Here I would have e to the t, which is a lot nicer. It's a lot closer to the rule than not, right? You make a substitution to make things look closer to the basic generic rules that you memorized. What you will be left over with is an x squared, but your x squared is t. So by first doing a substitution, we end up with that. And that is, I think that was like example A that we did. So we actually, at this point, we probably know what this is by heart already. E to the t minus e to the t, t to the t minus t to the t plus c. And then I just replace that. Remember your training grasshoppers. I give you the rules and strategies for a reason. First thing you need to do, you need to memorize all the rules. You need to know them exactly. Because when you're looking at a problem, your first goal is to, what rule can I fit on top of this with like, literally like a template? It's going to flush right on top of it. If it doesn't happen, you need to do something to kind of create that situation. Another thing, the second thing you need to do is to know the strategies. Know when you would actually try an int by parts versus try a substitution versus try something else, which I gave you the first 3 steps. Substitution is step 3. Integration by parts is going to be step 4 or later. Substitution should cross your mind before integration by parts every single time. Yeah?
So it said x to the 3, but how do you substitute t? What do you do with the x to the 3rd?
I substitute t equals x squared.
Yeah, but after you do a t dt, you will have...
Well, the x to the 3rd is x squared times x. Right? The x, the substitution took care of it. I'm left over with the x squared. The x squared is actually t. So that's here. And this you can do by parts if you need to, but you probably wouldn't need to at this point. That's your answer. E integral of x squared e to the x cubed. What do you think here? Get another green chalk. Ideas? Yeah.
Try to make a x cubed to a single variable using U-Substitution.
Right, same idea. E to the x cubed, complicated. Don't want it to be complicated. Let's do that. Then my dt is going to be 3 to the x squared dx. And hey, you have the x squared right there. So the integral becomes 1/3 the integral of u. And look at that. That's a basic rule. I actually don't need anything more complicated. So that's your answer. Now, of course, if you'd immediately try to jump into by parts with that, you just make your life needlessly complicated. You didn't need by parts here. Okay, first step.
I did a U-Substitution with a different variable.
What would you substitute?
T squared equals x. What I did.
Right. Why?
Because cosine of square root of x is like
Complicated, right? You know how to deal with cosine. Cosine of squared x makes that complicated. Why is that complicated? The square root makes it complicated. Cosine of x, easy peasy. Cosine of x, radical x? Cosine of x squared, cosine of x cubed, cosine of x, any other. Crazy. Why would I have to deal with that? My first thing is going to make that guy behave. So yeah, I'm going to do t equals the square root of x, or better yet, t squared equals x. This means that 2t dt is going to be my dx. And I'm going to now plug that in. So now I'm going to have this cosine of t. So I got that guy to behave. My dx is going to be equal to 2t dt. And you'll notice that I have a radical x left over. What do I do with that?
Just t.
It's t. So now, this guy becomes, well, 2 times integral of t squared cosine t. How do we do that integral? Huh? By parts. Okay. So you can either do integration by parts twice, or you can do tabular method. Which, since I would need integration by parts twice, like I'd probably use tabular method personally. Stop when you hit the 0. Keep integrating this guy. Integral of cosine is positive sine of x. Integral of that is negative cosine. Integral of that is negative sine of x. So this is going to be equal to 2 times, don't forget the 2 from here,
T squared.
this times this, minus this times this, which now becomes a plus because of that, plus this times that, which stays a minus. And of course you'll do the integral of this times that, which is the integral of 0, which is 0 plus c. And so now your t squared is x. And that's your answer. Is that clear? Yeah.
I can make the 2 factored. Is that fine for you, or would you rather have it simplified all the way?
That's fine for me. Yeah, I wouldn't mind either way. It's not going to be much of a difference. Other questions? Anyone totally confused?
I have one question.
Yes.
So in the, we go from, when you substitute the t, you get t cosine t times 2 dt. Why are we keeping the 2 dt? Where does that come from?
Well, the 2 dt comes from us changing the dx. Right? Dx is this.
Right.
So this dx is that.
Oh, okay, gotcha.
Yeah. Other questions? Okay, let's move on. G. Now there was one very similar to this. I think on one version I changed the sine to a cosine, but either way. Yes,
U-Substitution.
with?
X squared.
Now we're getting it. Right. This guy is x squared times x. So my x dx is taken care of by the 1/2 dt. I would have sine of t. And then after that, I'll be left over with x squared, which is t. So that's just a guy where you need integration by parts once, where this guy is the guy that you're going to differentiate. So it's going to be u times v minus the integral of v du and that's going to be equal to t is x squared. And integral cosine is positive sine. think on the quiz I made this a definite integral, but if you had gone through this, you would have known most of the problem already. You just plug in the limits at this point. Tan inverse. Ideas. What would you substitute?
And the derivative from 1 over x squared minus 1.
1 over 1 plus x
yeah,
squared.
x squared.
So you want to do a substitution?
I mean, by part.
By parts with u equals tangent? Right, so this is very similar to the sine inverse function. Now yes, you might have considered substitution to begin with, but of course once you actually do the substitution, you get that 1 over 1 plus x squared. What are you going to do with that? Right, substitution is not going to work out for you. So this is one of those by parts where you only have one function, so you think of the u as your tan inverse and your dv as just 1. Your du is going to be 1 over 1 plus x squared, and your v is going to be x. And so this ends up being u times v minus the integral of v du. How do you do that integral?
U-Substitution.
Substitution, right? U equals 1 plus x squared, your d is going to be 2x dx. You're going to have to factor out the half, but ultimately you're going to end up with 1/2 ln of 1 plus x squared. Did a substitution here. U equals 1 plus x dx. We'll eventually get there. That's it. So ultimately, once you go through the strategies, you learn the rules, and you really practice using the strategies, the integrals shouldn't be too bad, because God knows in this class you have bigger things to worry about. We'll get to them, don't worry. Like eventually you're gonna like, please, just give me an integral, no more of this stuff. So you want to get integrals under your belt as quick as possible, and the quickest way to do that is to follow the strategies that I told you, which as time goes on we'll be adding to the strategies, how to recognize when to do what. In the meantime, let us move on to the next section, which is 8.3. So right now I'm going to teach you about doing trig integrals. Right? We're going to specialize in doing integrals involving trig functions. And the main idea here, I suppose if you can sort of come up with one, use trig identities to help us solve integrals. Let's actually just jump in. Okay. Let's start with an example. How would you do that integral? Huh? Separate them? Separate what?
Something. Let's take it out, and then we have actual tangent.
You mean multiply two tangents like this?
Sine square over cosine square.
Sine squared over cosine squared?
Yeah.
Okay, what are we going to do with that?
Substitute.
not going to work. What's the issue here? Because the sign is squared, it's not going to work. So you substitute u equals cosine, your d is going to give you one of those signs. You're going to be left over with a sign. What are you going to replace with? The radical of 1 minus u squared. It's the worst situation that we started with. Not that it's impossible, I'm going to teach you how to do an integral like that, but that's a couple sections away. Yeah?
You do the integral of secant squared x minus 1 because it's an identity.
Right, it's an identity. The whole point is to use a trig identity. Tangent squared is equal to secant squared minus 1. Now at first that might look a little bit worse, but it's actually not, because you should already know what the integral of secant squared is. What is it? Tangent. How do I know? Because the derivative of tangent is secant squared. 1 x. And there was some confusion last time about that. It is x because of the dx. Right? That tells you who the variable is. So, integral of 1 du is actually u. The integral of 1 d theta is theta. The integral of 1 dp is p. The integral of 1 dx is x. Right? It's x because of the variable here. Yeah, so that's basically it. Tangent x minus x. Okay. Here's a useful one. Integral of tangent. How would you just, if you just had tangent, what would you do here? Yeah.
I'll substitute sine over cosine x dx. And then let u equal cosine x. And then so du should be negative sine x dx.
So now your substitution is going to work because you don't have a sine squared, you just have a sine. And so that will give us minus ln of absolute value of u plus c, which is, in this case, cosine x. Also, I want you to note something. Remember back in when we learned about log rules, we can take products, multiples of a log, and bring it up as a power. So another way to look at this is to write it as ln of cosine of x to the minus 1. But of course, absolute value of something to the minus 1 is the same as the thing to the minus 1 absolute value. So this is really just 1 over cosine absolute value. Let's get absolute value of secant. So some people don't find the negative sign in front of there not really aesthetic. They prefer to remember it this way. In either case, whichever way you choose to remember it, you need to remember one of them. This is now one of your basic rules. A new inductee, something that you need to know by heart. And I asked that in the bonus. You could have figured it out, or maybe you knew it by heart already. So now, this is something that we know now. Or, if you want, just pick your favorite version, remember that. But remember one of them. Another useful one. On the secant. So we now know how to integrate cosine, sine, tangent, and secant. Well, we're going to know how to integrate secant now. We're kind of going through all the trig functions. We're not going to go through all of them. But secant is one that we need to know. Ideas. 1 over cosine. Where can you go with that?
Values that are on ln cosine.
Can't get an ln in there.
No.
You could make it cosine to the negative 1.
Okay. And what do you do with that?
I don't know. 5 parts or something. Is it the
Okay, so this one's a weird one. I'm going to tell you how it's done. And frankly, I don't even know how the person who came up with this came up with it. It's like, this is traditionally how this integral is done. We're going to do one of those sneaky math tricks where we're going to multiply and divide by something convenient that's going to make this actually a little bit nicer. And the thing that we multiply and divide by, believe it or not, is going to be the following. This is weird. Like, how did this guy come up with it, right? What is this? And at this point, you must say, you must be crazy. You're making it look more complicated. Is that more complicated? Yes, it's more complicated. Is it, though? Do you guys see it? You see it? If you let u equals secant x plus tangent x, what is your d? Derivative of secant? That's secant tangent. Derivative of tangent? Notice anything? Oh! Like out of nowhere, right? From left field. Like, yeah, this guy, by doing this multiplication division thing, it turns into a 1 over the u integral. And that's the answer. And yeah, at this point, just memorize that. Like, I don't expect you guys at this point to be able to come up with little tricks like that. That one was very sneaky out of left field. But that being said, this is now also a basic rule. It is something that you are expected to know. So, if you want to add that one in there. It was also in the bonus problems. Which, by the way, I don't remember if I actually mentioned this, but how quizzes work, I always have a bonus section to the quizzes. The bonus section will cover things I'm about to teach that I haven't yet taught. So a way to actually try to, you know, give incentive for people to read ahead. You know. So things I'm about to teach, I'll put like them in a bonus section. And how that it will actually work, grade-wise, is, for example, this quiz here was out of 10 points. And I believe, was it out of 10? I don't remember. So you pretty much get 1 point for each answer. 1, 2, 3, 4, 5, 6, 7, 8, 10. Yeah, so this quiz was out of 10 points, but there were 1, 2, 3, 4, 5 bonus problems. So that means you could have gotten 5 points extra. So now let's suppose someone actually did extra. Let's say they got all 10 problems correct on the quiz. And they got some of the bonus problems, right? Like 3 of them, right? So they got 13 out of 10. What does it mean to get 13 out of 10? Well, what I would do is I would give you 10 for this quiz, so you get 100%. And then those 3 points, I'll save them, right? And then I can add them to another quiz somewhere else. So let's say you mess up on some other quiz. I can take those 3 points and add to that other quiz. So you can get a little bit of cushion here and there. So in addition to that, I'm dropping 2 quizzes.
Jhevon,
Plus,
for
yes.
people who get like 5, 6 out of 10 on the on the quiz that we took, and however got all those questions, whatever you got
The
from
bonus?
the bonus correct, what's gonna
Yeah,
happen?
I'll add it to the grade.
You'll add it to the
Yeah.
6 plus 5.
So let's say someone got 6, and then they got all the bonus problems, right? So they got 5 from that. They got 11 total. So I'd literally give them 100% for that quiz, and they'll have 1 point extra to add to some other quiz. Yeah. So it pays to read ahead. You know, I definitely want to encourage that kind of behavior. So, yeah, so this now another one of our basic rules. This is another thing now that you know by heart, right? So from now on, you know that the integral of secant is ln of absolute value of secant x plus n. Okay. Now that being said, word of caution, just so you don't waste your time. In moving forward, the cosecant and the cotangent functions will be largely ignored. Right? Now, of course, you need to know some basic idea of how these guys behave. Like, you should know that a cosecant is 1 over sine, and a cotangent is 1 over tangent, or cosine over sine. But in terms of calculus, in terms of knowing how to integrate them, don't worry about it. We're going to actually ignore it. So pretty much all the rules that have to do with cosecant and cotangents, you can ignore it. In fact, deal with cosecant and cotangent, they actually behave very similarly to tangent and secant. So rules for cosecant will be very similar to rules for secant. In fact, to integrate cosecant, you'd actually multiply by cosecant plus cotangent over cosecant plus cotangent, blah, blah, blah. And to do the integral of cotangent, you'd first write it as cosine over sine and then do a U-substitute for sine. Pretty much any tricks that I teach you to deal with tangent and secant, analogous tricks are going to work with cosecant and cotangent. So we tend not to test you on those, right? If you know how to deal with secant and tangent, you'll know how to deal with cosecant and cotangent. And so we just automatically, we'll assume, by teaching you everything you need to know about these guys, you'll automatically kind of know about those guys without us having to test them. So just so you know. So if you're practicing a bunch of problems and you come across problems where there are a bunch of cosecants and cotangents, just ignore it. I don't know, I didn't pick the homework problems, the math department did, but if one of them show up in a homework problem, yeah, get through that one. But I'm never going to quiz you or test you on one of these guys directly doing calculus, unless it's really some like basic elementary trigonometry. But even then, I'm not going to put these guys on tests, so you can actually ignore them. So what we are going to do next is we're going to learn how to deal with integrals that deal with cosines, sines, secants, and tangents in various forms, right? And the assumption is, again, you'll know how to deal with cosecants and cotangents if you can deal with secants and tangents. So we now deal with integrals. Of the forms. So this section really focuses on these classes of integrals over here. So the first class of integrals that we need to know how to do is if you have products of sines and cosines. If you have products of secants and tangents to some power. We're going to deal with the integer power cases first. But more generally, this is functions of sines and cosines. Right, where maybe they have non-integer powers or something like that, or we throw a radical in there or some random division somewhere. And the same thing with functions of secants and tangents. Again, another warning, just so you know what to expect. These two pieces over here, largely by osmosis. I'm really going to teach you about these two cases over here. And then, the lessons that you pick up over there, you'll be able to kind of apply them to something more generic. I might give you a couple examples of more complicated things, but we're going to deal with the nice integer cases first. That way you get comfortable dealing with the functions, you kind of know what to look for, how to apply substitutions, that sort of thing. And that skill should carry over to something else. And again, more than likely you're going to be tested on this case as opposed to some really crazy case. But usually, if you're in one of these two situations, previous integration techniques are going to help you out. So substitutions by parts, other techniques can help you out. So right now, let's actually deal with these So let's focus on 1. Sines and cosines. So I think for the rest of class time, we're going to focus on this type of integral. So you notice that there are several cases. In fact, there are 4 distinct cases that we can find ourselves in. 1, m is odd, n is even. 2, n is even, n is odd. And of course, as you might guess, these 2 are very similar. In fact, once I tell you the techniques for one situation, then you just switch the roles of sine and cosine, and you have the techniques for the other situation. You're going to have a situation where m is odd and n is odd. And of course, when both are even. Now remember what odd and even means. Sure. Plus or minus 1, plus or minus 3, plus or minus 5, etc. And even. 0 is an even number. Plus or minus 2, plus or minus 4, plus or minus 6, etc. Let's start out with case 1. So here's a strategy for case 1. You find yourself with viewing the integral, which is a product of sines and cosines, and you realize that the power of sine is odd, the power of cosine is even. Steps you're going to do is you are going to save a factor of the sine function. The sine is the odd one. You're going to pop one off and just put it to the side, right? 2. You're going to change all other signs to cosines using the Pythagorean identity. Cosine squared plus sine squared equals 1. 3. You're going to do a substitution. Equals the cosine. You are going to, of course, get a du is going to be a negative sign, which is going to get, you're going to put this guy in use that you saved in step 1, and then because everyone else is in cosines now, you're just going to have a function of u to integrate. Integrate. Right? At that point, it should be self-explanatory. Your training should kick in and take over. So. Two integrals like that. So the integral of sine cubed cosine squared. So this random integral shows up. You notice that the power of sine is odd, power of cosine is even. Of course, after you go through the 3 steps, is this the basic rule? Can I do no, okay. So now, essentially we're in step 3. You're going to want to see if a substitution can work. And it turns out in this situation, substitution can work. The first trick is, though, you need to save one of the cosines. This one of the sines. So I'm going to pop off a sine and just leave it at the end. That is going to be your first step. Second step, you're going to change all other sines to cosines. So this is a sine squared. You can now change that by 1 minus cosine squared. And at this point, third step, substitute. U equals cosine. your du is going to be minus sine of x dx. So you are going to get the integral minus the integral of 1 minus u squared times u squared du. And that's an easy integral to do, hopefully. What do we do here? Huh? You expand. So we're going to get then power over to the 5th over 5 minus u cubed over 3 plus c. And u was cosine. Cosine cubed. C. And that's your answer.
Wouldn't it be u squared minus u to the 4th?
There's a minus on the outside.
You switched to
Professor,
Yes.
what do you do with the x sine x dx that you put on the side?
There's no x sine x.
No, the top.
There's a cosine squared.
Yeah.
There's a sine x dx.
What do you do with that? Oh, okay.
That becomes minus d. So that's a u squared. This is a u squared. Sine x dx becomes my minus d. So now you just get an integral in terms of u's. Usually you'll be able to expand. Just gonna, at this point, just expand using algebra and then do the power rule.
You don't have to apply the minus signs after.
I did. I actually did. So if I did this, it would be minus the integral of u squared minus u to the 4th. And the minus sign is why I turned it around. Other questions? What's going to happen to sine cubed?
So you do the same thing, drop off on the side.
By the way, you could appreciate here that the power of cosine in this integral is what?
0.
0, which is even. So technically, even if a cosine isn't there, it just means it has an even power. So you're still in case 1. 0 is an even number, which is why I wrote it down. So technically, you have a cosine to the 0th power here. That's why it doesn't appear, but you're still in case 1. The power of sine is odd. So leave one of those guys. Change the other ones to cosine using the Pythagorean identity. U equals cosine. So that gives you u cubed over 3 and c plus c. That's case 1. Whenever you're in a situation where your power of sine is odd, your power of cosine is even, you save one of the signs. Change all the other signs to cosines, and then do a u equals cosine substitution. Case 2, very similar. Just change the roles of sine and cosine. In case 1. You might not need an example, but let's do one anyway, just to be thorough. first step?
Take out a
Yeah?
Say a factor of the cosine.
Say a factor of the cosine. Second step.
Change all the
Change all the cosines to sines. So I save this cosine. I want to change these cosines into sines. How do I change cosine to the fourth to sines?
1 minus sine x squared, parentheses, and squared at the end.
Right, cosine to the fourth is just cosine squared squared. You know how to change the cosine squared because you have that rule memorized. And then you just square that at the end. So you have that. And of course, next step. U equals? Your du is going to be cosine of x dx. So this just becomes u squared minus u squared squared du. What do we do now? What would it look like? What happened at this point? It's hot.
So it'd be u squared, open parentheses, 1 minus 2u squared plus u to the fourth. We multiply that out.
U was sine of x. Let's turn to it. Questions on that one? Same strategy, just took a little bit more algebra. Case 3. Say both are odd. Like you have a sine cubed cosine to the fifth and you want to integrate that. Step 1. You're actually going to apply a similar strategy as above. You're going to save one of the odd powers. You're going to save a factor of the trig function. With the smaller power. We'll get back to that. Why the smaller cube. Change everyone else to the other trig function, the one that you didn't save. Three. Substitute u equals other trig function. integrate. Yes?
Why did it change from positive to negative for U7/7? We changed it from.
Oh, it's not supposed to.
Okay.
Let's do an example. Let's do an example. So add that. That we just mentioned. Okay, step one. What? Save a what? Who's the smaller power?
Cosine.
3. Okay, save one of those guys. Second step. Huh?
Anything else to sign?
You need to change the sign to cosine. Change everybody else to the other trig function, the one other than what you saved. So you're gonna, this is 1 minus cosine squared. Now you do a substitution. U equals that other trig function, cosine. Your d is going to be minus sine x dx, and you'll end up with the negative 1 minus u squared to the 5th dt. This is equal to, I'm going to distribute the negative while I'm expanding, so that's u to the 5th minus u to the 5th, and this is going to be u to the 7th. So you're at u to the 5th minus u to the 7th, and I brought in the negative sign. And this one, that's u to the 8th over 8 minus u to the 6 over 6 plus c, where my u is cosine. Now, let's deal with the y to smaller. It turns out you could actually do the opposite of what I did here. But what would have happened? Let's check it out. That's sine cubed x. Let's say I saved one of those and put the cosine at the end. I would have to change the cosines to sines. Time you do a u cosine, so I would end up with u cubed 1 minus u squared squared du. And you'll notice that this is harder than the last one. Because here, I didn't have to expand this square. Whereas here, I do. Turns out that if you save one of the bigger powers, it means more expanding, right? So it's not like you wouldn't be able to get to an answer, you would, but it can be much more annoying. So for example, if this were cosine to the 11, right? Then I factor off 1, I'm going to have to raise this to the 5th power. Very annoying. Whereas if, even if that were cosine to 11, what's going to happen to me here? Like that becomes 11. Still not a big deal, right? Or becomes. So it's not going to, it's nicer to actually save one of the smaller powers. Makes it easier. Waste less time. Quizzes and tests are short. to save as much time as possible. Case 4. What if both are even? Well, you use, let's call them double angle formulas. They're exactly the same as the half angle formulas, how you want to look at it, I guess. So, remember what the sine of 2x is? What the cosine of 2x is? Sine 2x? Sine, cosine x. Cosine of 2x. Give me another way to write that. Give me another way to write that. Okay. Now, what's important for this technique are these, or you need to know this anyway, but this in particular is going to be important for this technique. Be a little bit more specific. These in particular is going to be important for this technique. The idea is here, I can actually solve for a sine squared and a cosine squared. And this can just be something that you know now, just know off the top of your head, it's going to be nice. If I were to take this equation and solve for sine squared, it means I can replace sine squared with 1/2 1 minus cosine 2x. And I'd be able to solve for cosine squared, right? That is 1/2 1 plus cosine 2x. Not new things to memorize, just things I want you to know that I don't want you to forget. You should have memorized this since pre-calc and calc 1. So, we have these formulas. That's pretty much how you're going to do it. If you see a sine squared, and they're only even powers of trig functions, you're going to change it into that. Same thing for cosine squared. Let's say you have a sine to the 4th. Well, this just means sine squared squared. So you're just going to square this guy, right? And if you get squares out of here, you're going to expand them again using the same formula. So you're going to apply those. Let's actually do some examples. How would you integrate sine squared? How would you integrate cosine squared? And if I show you sine squared, I'm not going to show you cosine squared. It's silly. Left to the rear. Let's see. What if I have cosine squared times sine squared? D. What if I have sine to the 4th cosine squared, etc. So for whatever reason, you need to know what the integral of sine squared x is to solve some problem, right? Some bigger problem. How do you actually go about actually finding that? I've done that before, of course. So I'm literally going to replace sine squared with that expression. And look at that. Turns out that's a lot easier to integrate. Integral of 1, x, integral of this. Right. technically a U substitution was supposed to happen here. You had to do U equals 2x. At this point, I expect you to know if your D is going to be a constant, you just divide by that constant and just apply the rule to the outer function. Doesn't work in general, that only works if your U is a constant, right? So the integral of cosine 2x is sine 2x over 2. The integral of cosine 7x is sine 7x over 7, etc. Don't expect you to have to do a U substitution for that. But do it if you have to. You know, it'll take you a few seconds longer, but you don't want to get it wrong either. Yeah, that's actually it. That's how you integrate sine squared. Cosine squared, pretty much the same thing, except you have a plus sign here and here. Let's see.
Rewrite the sine squared.
What now? I don't know. Why the half measure? Do both of them. What's going to happen now?
They're just going to expand or limit to each other.
So there's a quarter. 1 plus cosine 2x and 1 minus cosine 2x gives you what?
So you have 1 plus negative cosine 2x squared.
1 what?
1 minus cosine
1
2x
minus cosine 2x squared. What's 1 minus cosine squared?
sine.
It's actually sine squared. Right? Now, another way you could have seen that. Double angle formula. This is actually cosine of x sine of x all squared. What is cosine x sine x? Well, that's 1/2 of sine 2x. Square the half, you get the quarter. Square the sine 2x, you get this. So, could have gotten here a little bit quicker, but hey, we're here. Let's actually continue. How do I deal with this? Yeah.
Where you said cosine squared 2x, if I use the double angle formula again, and I can get that answer?
What, this?
Yeah.
Yeah, you'd end up with the same thing at the end. It's not going to look like this. You'll end up probably at the next step. So now you have sine squared of 2x. How do you deal with that? Let's take that little switch here. How do you deal with the sine squared of 2x? Yeah?
You could rewrite it again in terms of 2x.
As?
As half times 1 minus cosine 4x.
So that becomes 1/8. 1 minus cosine 4x. Integral of 1?
X.
Integral of cosine 4x?
Sine is 1/4 sine.
Sine 4x over 4. That's the integral for that. Yeah, and that's where I stopped with my last class, so we're stopping here. We'll pick up, try the last example. Sine to the 4x cosine squared. In fact, try many more examples. Okay, look up in your textbook, try some harder ones. Maybe even, I didn't tell my last class this, but you guys are cool. Maybe, just see if you can handle one of the quirky problems. Whereas, just based on what we've been doing so far, you should be able to figure this out if you just know how to deal with sines and cosines in general. So that's let's see if you're learning by osmosis as the plan is. Let's actually try that one as well. And we'll pick up on that on Thursday.